Alright everyone, welcome to another Physics QBit. In this video, we'll dive into conceptually understanding what an electric field represents. I know that the idea of an electric field can be really confusing when you run into it for the first time and really abstract, and so I just wanted to take some time to explain what it represents exactly and why it's like calculationally useful. Alright, so before we talk about the electric field, I wanted to take a second just to discuss what a field is, because it's actually like a formal mathematical idea, right? So a field is a region of space in which every point is assigned some value. This value can be basically anything, but in intro physics, we'll really encounter two kinds of fields. The first field is going to be a scalar field. And as you may be able to guess from the name, every point here in a scalar field is assigned a scalar value. And so this sounds kind of abstract still, but I'll bet you've already seen a scalar field in real life actually. So go back to remembering, watching the news or the weather or whatever, right? And sometimes they give you these little maps. So I'm gonna make a little cartoon map of Colorado because it's a nice square shape. Okay, and I'll bet you've seen these maps where, like, for example, maybe it's warm up in the northeast of Colorado, so it's like 92 degrees here, and it's like 85 degrees elsewhere, and maybe like 78 degrees here, and like 63 degrees here in like the bottom left part of Colorado, right? But you've seen these maps where like these parts are all colored, right? So such that the color corresponds with temperature. So basically every single like pixel on this map is assigned a color, and that color is really just a scalar numerical value for the temperature at that position, right? And so this would be a scalar field because every single point in Colorado, every single location in Colorado has been assigned a scalar value. The other kind of field that we might run into in intro physics is what we call a vector field. Vector fields are fields in which every single point is assigned a vector value. So this one's harder to imagine, but for example, if you were a hydrologist and you were studying rivers, right, you could make a vector field that maps out the current in different parts of the river. Let's say, for example, this is a little river, right? And you have a little machine that can detect how fast the water is. And maybe you can make a little map that shows that after measuring all these currents, you find that the current is strongest in the middle of the river. In other words, the water is flowing fastest. And so every single point here in this kind of map is assigned a vector value where the vector corresponds with the velocity of the water at that position, right? And so this is an example of like a vector field here. And so like you can find some interesting things in vector fields. So like, for example, if there was a rock, you might find that there's some kind of like funny eddy currents around this rock, right? Something like this. And so the idea is a vector field gives you an idea of what some kind of vector quantity looks like all throughout some kind of region of space. It turns out electric fields are this second kind of field. Electric fields are vector fields. Before actually talking about electric fields, I think electric fields are abstract enough that one good way to understand them is by analogy, okay? So we're gonna use this analogy of like an ocean wind map. So imagine for a moment that you wanted to sail on the ocean and you had a map of like the wind at different points on the ocean, right? So we have this vector field that at every single point on the ocean describes the speed of the wind and the direction of the wind. Let's say we are pretty wealthy, okay? And we have two sailboats. We have a small sail, and we have a boat that's red with a big sail. Okay, and let's say we were interested in understanding how safe sailing on the ocean would be by understanding how much force our sailboat might experience from the wind. We can see that the wind map is already pretty useful for this, right? Because we can see all the vectors that represent the wind speed, then we already have a pretty good impression of how strong the forces would be just from the actual vectors on this map here. But if we were to actually put in a sailboat at like a position here, right? Let's pick this one with the nice big arrow with a really high wind speed. We probably can predict that the small sail will experience kind of a small amount of force, right? Because the sail area itself is quite small, but the wind speed is still high, right? We could also try putting in this big sailboat, and because the big sailboat is experiencing the same wind but has a bigger sail area, it must experience a larger force, right? And so I really like this analogy for the electric field because in this case, right, the electric field is really the wind map. It gives you an idea of kind of how strong the forces would be, but you need to actually plug in a test charge, or in other words, kind of in our analogy, a sailboat, to understand the actual real measurable force, okay? So in other words, the electric field gives us an impression of the electrostatic forces without a specific test charge plugged in. And so let's go into this in a little bit more detail with the actual electric field and electric force formulas to kind of understand how this works. So once again, by analogy, right, electric fields are kind of our electrostatic wind maps. And so the wind on the ocean comes from a bunch of different factors, right? It's all about like air temperatures and fronts meeting each other. But in the case of electric fields, right, the thing that really sources an electric field is some kind of charged object. And we'll consider a point charge with charge positive Q source. And then we'll think about our sailboats as these little tiny positive test charges, positive Q test in purple here. By Coulomb's law, right, we know that the electric force between 2 point charges is K Q1 Q2 over R squared, or if we recast it in terms of our source charge and our test charge, it's K Q source Q test over R squared. And I've kind of factored out this Q test in a prescient way. We'll see why we do it this way in a second here. But in this case, right, the source charge is like our source of wind here, and the test charge is our test sailboat. If I plug in the little positive test charge at a bunch of different locations, I should be able to understand how strong the actual realized force on the test charge is, right? And so using Coulomb's law, I can tell that if I put my little positive test charge here, okay, it's going to experience a repulsive force like this. It's going to be pretty strong because we're pretty close to the source of the wind, right? Or in other words, the sort of source charged particle. Similarly, if I put it really close over here, I'm going to get another repulsive force kind of pointing to the right. And you can see kind of how this repeats for every single location nearby. So I'll go ahead and draw them. And in principle, these are all equidistant, so they should be the same arrow length. Right? So after putting my test charge in here, I can see that I'm going to get a really strong repulsive force really close by. Then if I kind of look at the positions farther away, right, the farther away I get, I'm going to have kind of an inverse square less amount of force because of this sort of 1 over R squared in Coulomb's law. So this is what the electric force is going to look like a little bit farther away here. Okay. But just like our kind of sailboat example, right, I don't have to use this specific purple test charge. I could have used another green, bigger test charge, right? But regardless of which kind of test sailboat I use or test charge I use, I can still see that there's a trend here. The closer I am to the source, the stronger the force is. In fact, I can even see that in the way this equation is written, right? If I look at this term here, this left-hand side term, I can recognize that this is all the stuff that I don't need a specific test charge to be able to write down. In other words, this kind of describes how strong the wind is, and I can figure out how strong the actual force is by multiplying the wind by the kind of size of the test charge, or sort of analogously, the size of the sail, as we were thinking about kind of earlier, right? And so this leads us to the formula for the electric field around a point charge, or how to compute kind of how strong the wind is near a point charge. It's just this left-hand side term here, this KQ source over R squared, right? If I use this formula, and so let me take a second and just formally define it. E equals KQ source over R squared. And I know we were talking about the electric field as a vector field. Right now, let's just kind of think about the magnitude here, right? If I wanted to compute the actual force, I can see from the equation above that the actual force here, Fe, is really just the electric field, okay, with these kind of full vector things, times the test charge I plug in. And so once again, kind of going back to our analogy before, it's like the electric field measures the wind speed, okay, in quotes, and this is the size of the sailboat. But once again, the point is, this equation here gives us an idea of what the wind speed is without having to plug in a specific test charge Q test, right? So this is why I really like this analogy for the electric field. I think it makes it a little bit easier to understand why we break down this formula in the following way. It can be really useful sometimes to have a quantitative idea of how strong the wind is, agnostic of any test charges you might be interested in plugging into a particular electric field, right? So the only other thing I wanted to do was talk about what happens if you have a negative source charge. So, like we kind of alluded to before, we think about a positive test charge, and that's because we have to have some convention to decide whether or not things are repulsive or attractive, right? Which depend on the sign of the test charge. So, when it comes to drawing the electric field lines, you always want to draw them assuming that you have a positive test charge. However, okay, when you're using the actual formulas, the formulas work for either positive or negative charges. Okay, so it's just the lines we draw with a assumed positive test charge, just to make sure that we have some convention that we're sticking to, that we can all agree on. And so when it comes to a negative source charge, right, there's only one difference here. Because the electric field lines assume a positive Q test and we have a negative source, we're going to have an attractive force, right? And so what that means is negative charges, negative source charges, I should say, have attractive fields. And by attractive, I mean pointing inwards. Because if I put a positive test charge near a negative source charge, right, the positive test charge is going to experience a wind kind of pointing towards the source charge here. It's going to be attractive. So, in other words, the electric field near a negative source charge is going to be quite strong and inwards if you're close to the source charge. And kind of similarly, we're going to have this inverse square effect. So the farther away you are, the kind of quadratically weaker this field becomes. Okay, so this is a useful little cartoon for remembering what the electric field near a negative source charge looks like. The formula itself is still the same, and so let's summarize our formulas again. Fe is K Q source over R squared times Q test, okay? Where the electric field, now with the kind of full vector symbol, is K Q source over R squared. And we also know now that it points away from positive source charges, okay? And it points towards negative source charges, right? The actual magnitude is the same in either of these cases, only the directions change for a given source charge magnitude. All right, so I think that's a pretty good place to stop for this video. We've covered kind of how to think about electric fields conceptually, and we've gone over kind of how to, and we've gone over the equation now that describes an electric field based on a source charge, magnitude, and sign. So let's go on to a summary for this video. Okay, so in summary, we like to think of electric fields as these kinds of like electrostatic wind maps. In other words, right, they give us an impression of how strong the kind of electrostatic forces are in an area without having to plug in a specific actual little test sailboat / test charge. The electric field formula comes from Coulomb's law. So Coulomb's law reads Fe equals K Q source over R squared times Q test, right? Where Q source and Q test are the 2 point charges that are interacting. K is Coulomb's constant, and R here in the denominator is the distance between the charges. And so the electric field, right, is this left-hand side term, which is written in terms of just the source charge and distance from the source charge. So we don't actually need a test charge. And formally, the electric field equation is E equals then K Q source over R squared. Like before, we saw there's a couple rules for positive source charges, right? This points away. And for negative charges, it points towards the source charge. Points towards negative Q source, right? The units of the electric field, I think, are easiest to see from the definition of the electric force like this. So Fe equals Q test times E. And so we can see in this structure, right, if I solve for the electric field, I should get units of force over charge. Something like this. Or if you want to write this in kind of the usual units, this is going to be in newtons per coulomb. And so from these units, right, you can tell the electric field gives us basically how much force we get per unit of test charge we plug into a particular position in space. This would be like if wind maps were presented in terms of newtons per, unit area of sail or something like that from our earlier example. If we plug in a sail area, we can figure out the total force, but otherwise it's kind of proportionally given in terms of whatever sail you might want to plug in at the end. And so the last thing I want to leave you with is these little cartoons for what the electric fields near point charges look like. So for positive point charges, we know that we have repulsive forces, since we assume that the kind of test charge is a little positive charge. They get weaker the farther away you are. So I'm going to draw a little cartoon showing what the electric field looks like near a positive charge. And these are repulsive, right? Because if you plug in a positive test charge, we're going to get a kind of pointing outwards force. There's one more here. Good. And conversely, if we have a negative point charge, okay, we're going to have a strong attractive force for any positive test charges, very close by to the point charge or very close by to the source charge. And as we get farther away, this attractive force is going to become weaker quadratically, thanks to that 1 over r squared in the electric field formula. Okay, cool. So I think that's really all I have to say for electric fields for this video. I also know in this video, we've only looked at the electric field from a single point charge, kind of one charge at a time or one source at a time. Next time, we'll talk about how to calculate electric fields if there are multiple point charges. And then after that, we'll work on kind of the harder AP Physics level question of how to compute electric fields from continuous distributions of charge, like an infinite line of charge or an infinite plane of charge or a ring of charge, something like that. As per usual, if you have any thoughts or questions about any of this stuff, you can feel free to share those in the comments section below, and I'd be happy to talk about them with you. This is also a good time to advertise that I do private physics tutoring online as well. So if you want to work with me privately on any of your physics courses, you can feel free to email me an inquiry at my email, which is listed in the description below. And finally, please don't forget to like and subscribe for more free physics problem-solving tips and tricks. This has been Physics Tutoring Quantized.